Okay, sorry about that. So let's see here. Okay, great. So I'm RJ Honicky, a grad student here at Berkeley, and today I'm talking about the NSMARTS project, which stands for Network Suite of Mobile Atmospheric Real-Time Sensing, which is my dissertation work. Some of the work that I'm going to discuss, however, was done by other people. Dick White and two of his students, Justin Black and Alec Eliam, worked on the particulate mass sensing that I'm going to talk about. John Canny and his student Reza Nima did some of the sensor board design for a different project that I incorporated into my work. Paul Wright and his former student Kyle Yeats did the phone enclosure design I'll mention. And we built some of the equipment I'll show with the Common Sense team at Intel Research, including Eric Paulus, Paul Aoki, Alison Woodruff, and Alan Mainwaring. And finally, Ron Cohen from the Atmospheric Chemistry group at Berkeley has also been pretty instrumental in our efforts in formulating our ideas. As Eric mentioned, he's my advisor, and this project was inspired by my former advisor and probably a friend of many of you, the late Richard Newton. So, in a nutshell, the NSMARTS project was driven by the observation that with the enormous proliferation of mobile phones we have at our fingertips, a global network with which to collect information about people's environments. And I think this really is a good segue from the panel discussion in that I'm thinking about instrumenting the world to understand it. So it's a kind of a good compromise between building and understanding. In our vision of the future, tens or hundreds of millions of mobile phones will be manufactured with cheap pollution sensors built right into them. Wireless sensor networks have had trouble delivering on the promise of ubiquitous sensing, mainly because of power and no economies of scale. And mobile phones solve both of these problems, and plus give you a network with which to transmit data that's already been built and works reasonably well in many areas. So I'm mostly interested in passive sensing, in which sensing happens without almost any intervention from the user. The Common Sense project at Intel, however, who I work with closely, also investigates more explicit and participatory, small-scale, democratic kind of sensing. Anyway, attaching sensors to GPS-equipped mobile phones would allow us to map the environment, since mobile phone users move around a lot. And it would also allow us to correlate pollution exposure directly with a particular person, again, speaking to the previous panel. And these are the kind of data that epidemiologists often lack. So sensing on mobile phones presents some really serious challenges, though. Users put their phones in their pockets. They would be indoors a lot of the time. They'll be in cars that emit pollution themselves. In other words, they do a lot of stuff that influences the response of the sensor. Also, cheap sensors will probably become miscalibrated easily, and users are unlikely to explicitly calibrate them. So we have to figure out a way to calibrate them automatically. Finally, inferring the user's context will be an important way that we can understand the data we get. Is the user in a car, indoors or outdoors? Are they biking, walking, sitting in their office? Is the phone in the pocket? Is it on the table? I'm not going to discuss this aspect of my research, but it's something that I'm working on as well. So why is this relevant to people in developing countries? Well, pollution in many developing world cities is far worse than the developed world. In fact, there was a recent study that said that up to 25% of China's deaths by, I think, 2033 will be due to respiratory problems, and something like a third of those are preventable with easy interventions. So as phones trickle into the developing world, if they have pollution sensors in them, we can understand on both a societal scale on the one hand and an individual scale on the other, at high granularity, just how bad things really are. So let's take a look at some data to get an idea about what it might look like. This graph shows the carbon monoxide levels that I was exposed to in Accra, Ghana in West Africa in January of 2006. It spans more than 2 weeks, so that the scale is pretty compressed, but time is on the x-axis there. And the spikes correspond to taxi rides I took, particularly the ones during rush hour. So 40 or 50 parts per million, which is this line here, 40 or 50 parts per million is not terribly dangerous for occasional exposure, but people selling stuff by the roadside, which you see quite a bit in many developing countries, are likely to have health problems from this kind of exposure. And this is particularly true when we examine the whole cocktail of air pollution that people are exposed to. So it's not just carbon monoxide, we're talking everything you can imagine probably. So here's some more data. This one taken in Guinea-Bissau. This graph represents my exposure in Guinea-Bissau in October of 2006. And most of these spikes also come from traffic, and they're same order of magnitude as the ones we saw in Ghana. But there's this one 300 part per million spike, which was from something different. So this is a ISP where I was working to set up some wireless links to rural community radio stations where the 300 part per million reading was taken. And this is the room where the generators for the ISP are housed. These are converted truck engines that you see. And the one with the big exhaust pipe in the foreground, right? This is an exhaust pipe. You notice that it doesn't go out of the room. And the one on the left, to be fair, is open. So it is exposed to the elements. So the exhaust does have a route to escape. But I took this 300 part per million reading at the door to the room. So presumably the concentration inside was much higher. I wasn't willing to find out though. The point of all this is that people are working in some very dangerous circumstances and might not even realize it. Once we discovered this problem with the generators, they stopped using it until they could tune it, and they also installed a carbon monoxide sensor to monitor their staff. The bottom line is that people in developing countries are particularly vulnerable to dangerous atmospheric pollution because of poor regulation, poor monitoring, and antiquated equipment. But we believe that they will do something about it if they have the right information. So in 2007, we decided to gather data a little more rigorously, and we put together a couple of kits with off-the-shelf data logging sensors and GPSs. So the one pictured here clips onto someone's belt and it senses carbon monoxide with this guy. And this one there's a couple of different similar sensors that can sense nitrogen dioxide, sulfur dioxide, or ozone, and this is a GPS. We gave 4 of these to university students in Accra. We also put together 6 kits with the same sensors that go in a ventilated tube that can attach to an auto. We gave these to 6 taxi drivers in Accra, and they drove around logging their location and pollution levels for 2 weeks. Here's an image of a mashup I did with Google Earth and the data that taxi drivers and students collected for us. The red dots represent locations where concentration measurements were made. The opacity of the color represents the number of samples that were taken, and so that the more transparent the color, the fewer samples that were taken in that or near that location. The white spots on the map are just clouds from the aerial photography, so that they don't have any significance. And the cool thing about this is that if you see its trouble spot, you can zoom in and take a look at what the area is like. And so I'll be demoing this this mashup in the demo following the session. Okay, here's let's see. So the next step is to gather data over a longer period to look at long-term behavior of sensors in the environment to see if we can correlate to other pre-existing environmental sensing mechanisms, and also get some practice gathering data from sensors and putting them into live databases. I can see I'm going to go over my 10 minutes here. So if you don't get a question you can ask me in the demo. What we see here is a prototype sensor board with 2 carbon monoxide sensors, a nitric oxide sensor, a temperature sensor, and an accelerometer for activity inferencing. This board connects to the phone via Bluetooth to give us flexibility in the mechanical design. So there's a Bluetooth radio, and that antenna obviously would not be in a design that was tightly integrated with the phone. Oh, that's not okay. Okay, well, I'll just talk about it then. Basically, what you would see here is an image of some street sweepers with a version of the board that I just showed you in an enclosure, which you can see in the demo. So it's probably not that tragic that you can't see it here. But we currently have 14 of these devices pictured, not pictured here, installed on street sweepers moving around San Francisco and sending back data. Obviously, street sweepers also have a rather biased view of the world, since they tend to avoid traffic, kick up a lot of dust, and produce their own pollution. But they give us an easy way to get good coverage. So this is a good first step towards having sensors in phones. And this slide is a different visualization that was mainly done by Eric Paulos, who recently left Intel for CMU. And I'll also demonstrate this for anyone who's interested. And our test platform will eventually be integrated with the phone by replacing the battery pack of the phone with an enclosure that has our board plus a battery pack. Here's a picture of the battery pack of the phone with a sensor board added. The enclosure has an orifice at the top to allow airflow to the PCB. And this is a view of with the outer enclosure made translucent. And obviously this is an initial design, and it'll probably take several iterations before it's ready to be usable on a phone. So switching gears a little bit, aerosol pollution remains the biggest environmental health risk for many people. And this is especially true in developing regions where solid fuel cooking, trash and brush burning, and old diesel engines prevail. Aerosol sensors have typically been quite large, but Dick White is developing a sensor that measures particulate matter smaller than 2.5 microns based on a MEMS device called Thin Film Bulk Acoustic Resonator, or FBAR. The FBAR is commonly used as a notch filter in mobile phones, so it's already produced in large quantities, and we understand how to make them. In our device, particles are deposited. So in this model here, there's an FBAR, and particles move through a chamber, and there's a heater here, and it causes the particles to precipitate onto the FBAR and change the resonance frequency of the FBAR. So it's a very simple and effective technique. And we found that actually it's almost as effective as much larger and more expensive sensors. And finally, we've done a test chamber where we can carefully control the concentration of poison gases such as carbon monoxide and nitric oxides and the humidity. And this allows us to test and calibrate the sensors and measure and characterize the noise that the sensors exhibit. So this is a plot of, one of the interesting experiments that we've done with our setup begins to look at how much we can improve the precision of the sensing system as a whole in cases where we sample quite densely in locations, such as when there's a lot of people in the same location in a crowd. In this plot, we can see the signal from one sensor in the dark dots, and the light dots, and one sensor in the light dots, and 6 sensors in the dark dots, and the signal from the 6 sensors is averaged, and obviously the variance of the signal goes down significantly when you do that. So here's a plot of the variance versus the number of sensors, and as you can see, it follows the 1/n curve that a Gaussian noise model predicts quite closely. Obviously, these results need to be extended to real-world situations in which sensors are not exactly co-located. And so I'm working on a couple of different mouse models, one based on Gaussian processes, another grid-based model as well that can take into account miscalibrations, wind, and other real-world factors. And I'd be happy to discuss those models in detail in my poster session. So in a nutshell, we've built a variety of platforms to begin to rigorously understand mobile sensing in the real world. We hope to have some really big and interesting data sets to share soon. Thank you.